Yeah, we can access it. It's there in the instruction set. Then Excel operations are really right. No, not Excel. You can literally select the bit position, read it, and change it. It's there. There is a instruction. Suppose you have to operate on. Yeah, you can operate on that bit itself. That's what you have to go to the register and how means you have to read the instruction set. Bitwise, bit fields. No need of cards, just encode and decode. And LTE standards. You have to do it in LTE standards. Not just a simple conventional code. Just yeah, yeah, we use conventional code in TurboCodes. There's so many other channel codes used in it, not just Turbo. Decoding Jesus.
ఊరికే 3 నిమిషాలు పోయే కదా అనిపిస్తున్నారు. పక్కన అక్కడే ఉన్నాను.
Okay, so this is the paper that appeared in IEEE Transactions and Communications in October '96. The major breakthrough paper. Okay, in fact, the conference version appeared, I think, 2 years before that. That would be in '94, I guess. Yeah, it's in May '93. In ICC '93, a conference version appeared. In ICC. Okay? So when this paper first appeared, people didn't believe it. Okay? People just said they must have shifted the curves by 3 dB. Okay? Nobody believed these results. Okay? Took them, you can see that, the journal version appeared in '96. Many people are not willing to accept this. But then people like the coding theory specialists like Dirsalar and many others, people at Jet Propulsion Laboratory in Pasadena, California, they implemented this algorithm. Of course, to implement it can't be done overnight. And then Benedetto did a very detailed mathematical analysis, and he gave himself and a few others. They gave a full mathematical justification. Still, TurboCodes, the math is. We're going to go through the probability of error analysis today, but some people think that it's more like a magic. Okay, you can get some bounds in the highest scenario, but for full TurboCode behavior, it's not easy to capture. Maybe there have been some recent advances. I'm not so sure. Especially it's an iterative decoder, right? So can't characterize the because equation is so clean. Unlike convolutional codes, you can describe the ISNR behavior very clearly. Then there is error flow phenomenon. The low SNR regime performance is not so good. The very low SNR, and then there is a short fall of the error rate, which is predict the possible. And then there is error flow. Okay. We'll go through it. You can also go through chapter 11 of Shortly. I will upload that. Chapter 11, that is basically book coding and decoding by Shortly. Okay. You can go through that chapter 11. Okay. There is one paper I would recommend. It is just for reference. This is by Robertson. Okay. Well, it discusses the map BCGR implementation. Especially in implementing the control codes, where the algorithm operates in log map. You have max log map version, and also there is a log map version. And you need to understand the three: full map, max log map, and the log map. There may be other variants, but these three are. And this paper, is a very good paper. It really compares and connects all these various methods. There is another fellow called Loganov. He developed soft output basically algorithm. Okay. And he also did a lot of work on iterative decoding, concatenation codes, codes. In fact, Berow's invention of TurboCodes, this big piece of work, largely owes to developments prior to that going to these set of people, they're French people, they were mostly interested in developing VLSI architectures for soft output decoding of convolution code and other programs. We are interested in the algorithms as well as developing VLSI architectures at that time. And while studying soft output Weitherby algorithms, as you can see, soft output Weitherby algorithm or map PCR algorithm plays a big role in the decoding of TurboCodes, which were introduced. Somehow they were inspired by this concatenation of two codes separated by Interleaver. And that in itself was not new. Forney had suggested concatenation of two codes long time ago, and it has been used. A convolution code as a rate of convolution code as an inner code, and a very high rate Reed-Solomon code as an outer code without interleaver has been used in many communications, so including IS-54 USD. Basically, you decode using convolution code and then with the residual errors, you correct them using another error correction code. Bring the overall property of error close to 0. The convolution code may bring it to 10 raised to minus 5, and then you put an outer code on top of it and bring the overall number close to 10 power minus 12. So this concatenation was there, but then if you separate two codes by an interleaver, the maximum likelihood decoding of this overall code is prohibitively complex, right? If you have two codes separated by interleaver, then maximum likelihood decoding is immensely complex. Then Hero and others, they developed this iterative decoding algorithm that approaches the maximum likelihood decoding. Not only that it approaches the maximum likelihood decoding, they constructed codes that indeed achieve very, very close to within a fraction. We'll see how. Then after the development of TurboCodes, again we have another class of codes called NDPC codes. NDPC codes were proposed long ago in the thesis written by this person? Gallagher. Yes, but the decoding algorithm was not developed at that time. Computation. Not available. Not a computation we have available today on the DSP process was not available. But anyway, some other people have revisited this channel code proposal. Gallagher and then have shown that you can decode NDPC codes with the iterative decoding algorithms. They also achieve performance very close to and comparable to TurboCodes. But they're quite different approaches. Alright, so before we give you the encoder structure for the TurboCodes and the rationale for proposing that particular structure, and before we give the property of analysis and associated receiver structure, first we need to learn something about recursive systematic codes, basically convolution. And they play a very important role in the design of TurboCodes. Okay. Even before that, let's consider a non-systematic convolution code. Do you know what it means by non-systematic convolution code? Yeah, see, in the convolution code that we considered in the previous two examples, the first bit, the output code word, in the output code word, the first bit same as the source code. And the subsequent code words are generated as a linear combination source bits. Okay. But in non-systematic convolution code, what we have is the source bits are dk. In systematic code, dk appears as it is, and then some linear combination of it will appear as the second coded bit. For example, in array. But in non-systematic convolutional code, we don't have that. This is the first coded bit, and then this is the second. So UK and BK form the entire code sequence. So this is non-systematic because DK doesn't appear here directly. Okay. So if I have to write it in D domain, I'll first write the expression for UK. Well, there is a polynomial G1I d k minus I equal to 0 to k minus 1. G1i's are, they take values 1 and 0. Okay. Similarly, Vk is equal to I0 to k minus 1 G2I d k minus I and G2I belongs to 0. It takes value is 0. In this particular example, G1I is noctal form, it's a 7, and G2I it's a 5. Okay, noctal. Okay. In D domain, let us call U of what is assumed U of k is U of D is equal to G1 of D multiplied with, let's say, the data D of D. D is a delay. So in this case, G of D, and similarly D of D is equal to G2 of D multiplied by D of D, and the code word U of D, D of D can be written in vector form as G1 of D, G2 of D, D of D. Okay? And G1 of D in this case is 1 plus D square, and G2 of D is 1 plus D square. Okay. So now, using this non-systematic convolution code, I will develop a related code, the recursive systematic counterpart of this code, that can be done by simply defining, well, this transfer function is G1 of D, G2 of D, right? The transfer function here is 1 plus D square, 1 plus D square, you see? Now what I'm going to do is, I'm going to divide this by 1 plus D square. Let's call it G tilde of this. This code, the code that we, of course, now this is in recursive form because this is IAR. This is impulse response is IAR. You can see it. Here the impulse response is FIR. Okay. So since it is IAR, we will have a recursive implementation. We will show the recursive implementation. Okay. Nevertheless, the distance properties of this code, the NSC, and the distance properties of RSC are very much the same. the minimum Hamming distance or whatever you call it, right? Hamming distance or sometimes float discussion will call them weights. Minimum weights of NSC and RSC are the same because you can see that they're very, they have some connection with each other. And the complexity of implementing the encoder and decoder are pretty much similar because the number of states in both NSC and the associated RSC implementations are the same. In fact, they share a very similar trellis structure. However, given an input sequence, the exact output sequence produced are not the same. Okay, given the input sequence, and we'll highlight the differences a bit more detail later. Okay, given the input sequence, the output sequence produced is not the same. Also, the first error event and second error events produced by these two codes are limited. Although they may have the same distance spectrum, there are certain differences. Okay. So you might say, well, I could have made this one and divide 1 plus d square by 1 plus d plus d square. That will give you another recursive scenario. You can use either one. Okay. So I will describe the one based on this realization. Okay. Where is this? Okay. We have dk here, the source. Okay. What is this AK, this intermediate variable? AK is equal to dk plus g to I equal to 1 to k minus 1. By the way, what is this k? K minus 1 is the memory of this. This case k equal to d k minus I. And g to I is 1, 0, 1. That is obtained from the NSC. Okay. Well, that is equal to dk. This starts from 1, right? 0, 1, 2. That is index I. So that will be d k minus 2. Okay. Now, I'm sorry. This is a k minus I, right? So, please correct this. Okay. Now you can check that this encoder obeys this property. Okay. So this can be written as a of d into 1 plus d square is d of d. Can we do that? Is it okay? And u of k is equal to well, a of k plus ak minus 1 plus ak. These are exclusive or operations plus binary arithmetic. That's why we have this. We don't have 1 minus d square, it's 1 plus d square. Okay. This gives us u of d equals a of d into 1 plus d square. Okay. And a of d is equal to d of d divided by 1 plus d square, and in the numerator we have 1 plus d square. And the transfer function u of d by d of d is 1 plus d square by 1 plus d square, and b of k is equal to d of k, that is the one here. So we end up with this formulation. Let's take that. I starts from 1 to k minus 1. I starts from 1 to 2. 0, so 1 has g to I is equal to 0, right? And this is 1. So this is dk plus ak minus 2.
From the picture, uk is equal to ak plus ak minus 1.
Oh, I missed one more connection. Sorry. Is it fine now? Yes, please. Okay. Okay. In the previous lecture, we studied the transfer function of a convolutional code, and we also studied the distribution of the three distance, right? So let's recover that. So the property of error for decoding of the convolution code using Iterative algorithm was expressed as the W of D is A of D multiplied by F of D, and P of D is the Q function something like that. Okay. What is A of D? So we had this all zero path code word, and then there is this an error event. Okay, A of D is basically the path multiplicity, right? The number of paths having the same Hamming distance or minimum distance with respect to the all zero code. Yeah. Okay, this we have described. Okay. And f of d is the number of ones the source bits corresponding to the all zeros are all zeros, and the source bits corresponding to this path has certain number of ones, and the total number of ones in the source is denoted as, in the source bit sequence is denoted as f of t. For the first error event, we have 1 followed by zeros, right? And for the second error event, we may have 1, another 1 followed by zeros, or 1, 0, another 1 somewhere else. So f of t is the number of errors, and a of d is the path multiplicity, and this is the union bound on the probability of error for the soft decision decoding of a convolution of code. Okay. We said the RSC and recursive systematic code, and the counterpart is, what is the counterpart? Systematic, non-systematic code. Okay. So these are counterparts. Okay. The minimum distance distribution, that is D free, and the next one, and so on and so forth, they share the same minimum distances for both implementations. But however, this W of D is different between these two cases. Therefore, the overall probability of error characteristics for NSC and RSC could be different. Okay. It turns out that in the low SNR regime, you know that in the high SNR regime, this D free kind of dominates the performance. Okay. In the low SNR regime, the bit error rate of RSC is generally less than that of bit error rate of NSC in the low SNR regime. Okay.
We can have systematic codes with feed forward convolution code.
See, here the issue is not the systematic part. The issue is the recursiveness. That whether it is FIR or IAR, that is the main difference. We'll show the difference. We'll expose it when we analyze this code. The question is whether it is FIR or IAR. That is the main difference. It's not about strictly the systematic, whether it is systematic or not. That's not the most important. Whether it is the process part of FIR or IAR. For high rate codes, especially for code rate greater than 2/3, the bit error rate of RSC is always less than bit error rate of NSC for any SNR. This plays an important role. Typically, TurboCodes operate with reasonably high rate codes because it's a code concatenation. The overall code rate may be half, but the component codes are generally high rate codes. Okay, but more importantly, it is the recursiveness that plays a very crucial role in TurboCodes performance. The recursiveness plays a very important. Let's now describe the turbo code encoder, turbo encoder. Just before we go any further, if we have let's say here, D of D, the input sequence is all zeros with a 1 in between. Let's take a code word. This is the source bits. All zeros with a 1 in it. And D of D is D raised to some number, right? Then what will be the output code word? U of D correspond to this input sequence. It has infinite number of terms unless you truncate the code and terminate it with 0. And this can correspond to, let us say, a single error event. So there is single one. This corresponds to a single error event. And the output code word has infinite long. Infinite long, it has lots of ones and zeros in it. And what is the total Hamming distance or free distance? It's infinity, right? So, in recursive systematic code, it's not the first error event that has the minimum Hamming weight. Now, let us say I have two ones this is 1 plus d square multiplied by some d raised to n, right? So I could have chosen this as 1, 0, 1, 0, 0. Let's take this sequence. What is the transfer function? 1 plus d square, u of d. And if I choose u of d as 1 plus d square, and what is output? What is Hamming distance of this code? Yeah, Hamming weight is, in this case it's, yeah, so it produces, Hamming weight is 3, right? No, it's not 3. And there is this. What is the code word? 1 plus d square. And another one is 1 plus d square. The Hamming weight is 3 here, but there are 2 ones here. Total Hamming weight is. See, this is the code word produced when the input is 1 plus d square. What is 1 plus d square? Basically 1, 0, 1, all zeros. This is the input. Okay. And since it has 2, 1, it corresponds to an error event of length. Basically, it's a second order error event. Okay. This is when the first order. So this is the first error event. This could be the second error event. And the code word is of this form. And if I have to come back into time domain and count the number of ones in it, 1, 2, 3, 4, 5. That is a total Hamming weight. Some ones, then the rest of them are zeros. Okay. So in the recursive implemented system RSC code, in fact, the probability of occurrence of first error event is nearly 0. Okay. But it is the second error event, the error event with weight of 2, that is u of d, with 2 ones in it, is the one that produces d free of 5 here. Following me? Okay. I think we have to go back to this diagram which we taught last time. How did we do it? There was an all zero code word, that is the code word, and And then if an error occurs, right, you deviate from this state, right, and then you rematch with the all zero error sequence at some point. Okay. Since this is a 0, this path corresponds to a 1, and then this corresponds to zeros, what we considered in the previous lecture. And this is the first error event. Okay. So the source has all zeros before this, and a 1, and then all zeros elsewhere. So that is this. Okay. At some point in the release, right? Before that, all zeros. So we talk about an error event. That's the first error event. Okay. This is the error event. Now, if I take the transfer function, this is u of d, that's input, and if I apply it, okay, to this particular code, in this case, u of d is 1. Okay, so therefore the output would be, in this case, let's call it d, right? Actually, there might be, if you start from here, you just take it as, from here it's d. You can rise to d raised to m, 1, some m. Then 1 plus d square divided by 1 plus d square into d is the output corresponding to this input of d of d. D of d is the input. D of d is d in this case. So if I come back in time domain, this code word, this is IAR, so it has infinite number, it's an infinite like polynomial. So the code word has a large number of ones and zeros. If I accumulate all of them, it has infinite number of ones. Of course, assuming infinitely long code. If you terminate at some point, it will fail to large. So definitely this is not the minimum distance, right? It's infinitely long. Okay. Well, you know that it's not minimum distance because when you take an error event of length 2, let us say, whose form is 1 0 1 0 0 0. That is, this is 1. There must be an error event 1, and then this is 0, and then another 1, and then it combines somewhere else. Okay? That is 1 plus d square. U of d is 1 plus d square. And if you give that as the input, we get 1 plus d square into 1 plus d square, divided by 1 plus d square, multiplied by 1 plus d square, goes away. And this is the code word associated with input 1 plus d square. And the total Hamming weight is 5, and that turns out to be the minimum Hamming. Okay? But for the convolution code that we considered at the time, the first error event produced the minimum Hamming. Here, first error event does not play a role. It's actually the second error event that has the minimum distance. Obviously, the input has 2 errors. Right? It has 2 errors. So, you can see that the error performance of RSC and NSC could be different because this rate W of D is different because this F of D could be different. Even A of D may or may not be the same. Okay. We'll bring back these arguments once again and analyze the turbo code. All we are doing is basically we have to understand the notion of the all zero path in the trellis and a path that deviates from the all zero path and rematches back at some stage. And there could be many error events, and associated with these error events, there is a Hamming weight and there is an input sequence associated with it, which comprises of certain number of ones in it. And the Hamming weight of those input sequence is the total number of errors, that is F of T. This F of T. Okay. The way the turbo codes are designed, the data D of K is here. Then we use the recursive systematic code RSC code 1, and it produces some output D1 of K, Then we take the source data and we interleave it. Okay? The same source data, it's interleaved. Then you put another recursive systematic code, code 2, and the polynomials of these codes could be the same or distinct. Okay? There's no need for them to be the same, but they could be same also. Okay? In this analysis, we consider them to be the same. Then it produces V2 of k. Okay? Of course, this U of k, you can transmit either this U of k, V1 of k, or U of k and V2 of k. This is a common part. And then we have a switch here that selects either one of them sequentially. One of them. See, it takes this, then followed by this, and so on. Okay? And what is the total rate here? Total rate? Rate of the code? Well, we are not transmitting all three simultaneously. We are selecting one of the two. It's right? Okay. So in a way, you take this data, you transmit using a recursive systematic convolution code V1 of k, and you interleave this data, and you send at a different time instant encoded using the same systematic, let's say the same RSC code, and another piece of coded information. So the code word, the ultimate code word that you produce behaves like a random code word because this is. Without that, there is memory associated in this V1 of k. Don't call it random code. Right? It's a linear combination. But here, because of the interleaver, the entire code word sequence behaves more like a randomly chosen code word. And if you choose this RSC polynomials properly, and if you design an interleaver, first of all, this code word has to be infinitely long or very large, and this interleaver has to be like a pseudo-random interleaver. Okay, it's like a random interleaver. Take a sequence of ones, and you take one bit and map it on this entire time scale somewhere at some point, distribute uniformly in entire length of it. So if you construct such a random interleaver, right, then this entire code behaves like a random interleaver. Okay. Not only that, okay. First of all, you may ask, why do you do this parallel concatenation? Why can't we could have also designed one code another RSC. I think there are some computational advantages in the decoding of this code, this architecture as opposed to this design it. Okay. In principle, once the data is received, you can these two codes can be implemented simultaneously. There is a high degree of parallelism. Okay. Some parallelism can be exploited by simultaneously running these two. So we will not study the serial concatenation for the time being. Let's stick to the original code architecture proposed. First of all, what would be an optimal decoder for this? Well, you receive the signal corresponding to UK, V1K, and V2K. Of course, this goes through, let's say, a binary modulation corrected by 8 to 8% noise. then you receive the signals associated with these three code words. Okay. And then you build this massive maximum likelihood decoder, right? That searches for the optimal decay that has a minimum distance compared to the received signal. But such a maximum likelihood decoder is very difficult to realize if the sequence decay is very, very large. Short sequence is perhaps good, but decay is very, very large. Very difficult to realize such a maximum likelihood. So we'll come up with an iterative decoder that we'll discuss later. Before that, let's talk about the properties of this concatenated structure.
Sir, for randomness induced by interleaver, helping in maximum capacity of making our turbo optimal.
We'll show that at the end of this lecture. We'll show that. Okay. First of all, we need to understand for this combined code, there is a weight distribution, the D-free associated with this. But in TurboCodes, D-free, maximizing D-free is not the sole criteria. In TurboCode, in convolution code, if you maximize D-free, generally, you can reduce the probability of error. Here, D-free is only a part of the scope. There is other elements. Okay. Here, there are two encoders. There are weight distributions are associated with this encoder, and there are also weight distributions associated with this encoder. So when you, for example, when you're dealing with this particular piece of first encoder, there is an error event that causes the minimum distance. Okay, we should make sure that this encoder does not simultaneously produce an error event with the same minimum distance error. If both occur, then you may decode this source sequence to the error. Right? When you're decoding one component code, there is an error event associated with that is the minimum distance error. But to make sure that for the same input, if you don't have this interleaver, if you use the same RSC, you will have the same minimum distance error event. So both will likely result in right? An error. But since there is an interleaver, the source sequence or the code word that you get, there is a source input and then there is a code word. And if the code word is the minimum distance, code word corresponds to minimum distance error event. Okay? Because we interleave it, it may so happen that we may not end up with the same minimum distance error event for this code. As long as both don't occur simultaneously. You avoid decoding. Make sense? So the design of this interleaver plays a very crucial role, and the fact that this code, these component codes are recursive also plays a very important role, which we will show it shortly. If they are NSC codes, then you don't get this advantage. That's all I want. Okay. Okay, let's see how this works. Let us say we have this decay is all zeros with a 1 in it. That means somewhere the source has a single error in the decoding product. And then associated with this decay, there is a code word. Okay? If the component codes are not recursive, what happens is that a decay of this form will always result in a minimum distance error. That is the first error event. That's what we have shown in the previous lecture, right? With a 1 here, you will end up with the first error event, and it has a minimum distance. It has a distance associated. If you take this sequence, you interleave it, still you end up with a 1 somewhere else. Then you will end up with a minimum distance error event associated with this interleave sequence. But our original design goal was not to make it happen. If there is a code word with minimum distance error event, we want to avoid occurrence of the code word with the minimum distance error for that component. Okay. So, if these were chosen as non-recursive convolutional codes, then we will not achieve that. Okay.
We have only one way, since the polynomial is prime 1 plus 2 plus b square.
Now, because this is recursive, if you feed this, the output will be IIR with infinite number of ones and zeros, and that is not the minimum distance error. And we have shown that a sequence with of this type, which is like 1 plus b square into some delay is there. There is here because there is a transformation. Okay, it's basically of type 1 plus b square. And the input with 2 ones, basically 1 plus b square form, produces a minimum distance error event here. Okay, but then what is the probability of this sequence after interleaving having 1 plus d square again? That's quite low because interleaver is an uniform interleaver. So after you interleave this will no longer have 1 plus d square form. Okay, so and the error event corresponding to this will not be the minimum distance error event. So the error events don't match in terms of having minimum distance error. Okay, so the recursive part of this component code plays a very crucial role because a sequence with all zeros and a 1 will not produce the minimum distance error. And since this is IAR, definitely you need at least 2 ones or 3 ones, whatever it is, depending on the code under consideration. In this case, a code word with 2 ones happens to be the minimum distance error rate. You may say, well, there are 2 ones, the error rate might have increased a little, but that's not very important. So the probability of occurrence of minimum distance error event has been broken up by the simultaneous occurrence of error events, minimum distance error events has been broken up by the interleaver. So the interleaver size, and that probability depends on the size of the interleaver and the structure of the interleaver. We want it to be a pseudo random like interleaver, as much as possible. Traditional block interleavers don't do a good job. Like read in rows, write in columns type. Interleavers don't do a good job. Okay. So I'll give you the probability of error analysis for this particular turbo encoder without even getting into the decoder. Okay. So it only takes a few steps. Okay. Then we'll talk about particular recursive decoder, and I will have you implement. Okay. So the realization is the code word transfer function. Well, the transfer function for RSC is 1 plus b plus b square by 1 plus b square. You can reverse this if you want, that would hardly change things. This is a 4-state convolutional code. And we'll assume same RSC as same encoder for the as constituent codes. We'll assume some kind of pseudo-random interleaver with uniform distribution. You'll have to actually look into this interleaver design a bit more carefully. Okay. As we already said, any bit stream with weight 1 so it's a 1 any bit stream with a weight 1 would produce an infinite string of ones and zeros, so the Hamming distance is infinitely large. Okay, so the likelihood of a single bit error occurring is basically 0. Okay, so we take a length 2 input bit sequence. So that is essentially something like this, and u of d associated with this, we call it u of d, right? The input, or d of d. D of d. Associated with this is no, I mean the first part is u of d, the second part is b of d, that is 1 plus b square d raised to m into 1 plus b square. Basically, this corresponds to the delay. Basically, the entire code word is d raised to m and d raised to m into 1 plus b square. Okay, we consider an block length of size L. Interleaver size is capital L. So therefore m could take any one of these values, right? 0 to L minus 1. This could occur anywhere. So many possibilities. Okay. For this parallel concatenation,
For the second one,
yeah,
the weight is 2 comma 1 plus b square.
what is that?
The second one.
Oh, this is the input. This is the input, right? So
1 plus b square into b square.
this is not the code word. This is basically this is length 1 input and length 2 input. Okay, or weight 1 input, weight 1, weight 2 input. Okay, and the actual code word is 1 plus. Let's leave it aside for the time. And we already said that for this case, it produces infinite strings of 1, and this is the one that we are really interested in. Okay. So the parallel concatenation would make an error if this 2-bit input error event, that is this, right? This single bit error event, this is a 2-bit error event. But to occur on one of the ports, right? One of the constituent ports, it occurs. And also, after deinterleaving, to correspond to d raised to f into 1 plus d square, where m equal to 0, 1 to l minus 1, within the period L of the interleaver. Basically, we call it deinterleaving if it happens on the second constituent code. After deinterleaving, again the code word corresponds to d raised to m into 1 plus d square for some m. If it happens on the first constituent code, then after interleaving, you end up with the source sequence again of the type d raised to m 1 plus d square. For the uniform interleaver, this simultaneous event happening on both sides measures.
It can't happen on both because we are switching between parity. There is a delay because rate half. You are having two.
No. See, you send this piece, and then next instance you are going to send another piece. There are two code words associated with.
But we are leaving one and sending only one.
Yeah, you're leaving one. See, you can think of having source bits and the coded bits of first encoded, first encoded. You can decode it. You can have source bits and second code bit as a second code. So you can think of them as two separate codes. Let us say this error event of length 2 happens on any one of the constituent codes. An error occurs on the second code, constituent code, if after interleaving the input has the same form. Otherwise, it will not get length 2 error event. Okay. What is the probability of occurrence of before interleaving and after interleaving the sequence is having this particular form? That's what is the and this simultaneous for the uniform interleaver, that is, there is a coded bit sequence, and you can take any one bit and you can put on any one of the other positions with uniform probability. The probability is the same. For the uniform interleaver, this simultaneous error event has the probability of occurring 1 divided by L chosen sequence. You need to choose 2 ones in a sequence of length L. Okay? Corresponding to 1 plus d square. Okay? That is equal to 2 divided by L into L minus 1. This is for one particular value of M. Now M can take L possibilities. So thus the probability let me make room. For a particular value of M. Taking the value 0, 1, all the way to L minus 1. For particular value of M. And thus, probability, that is L times 2 by L into L minus 1, that it could occur for any of L values M equal to 0 to L minus 1. Okay. That is 2 by L minus 1. Okay. Now we want to calculate the union bound on the turbo code performance, right? The original turbo code has then you switch between these two, right? But if you treat them as a single code word, it has a rate 1/3. Okay? The rate 1/3 has a D free of 8. That is 2 plus 3 plus 3. How do you get that? Well, the code word for the minimum distance agreement is 1 plus d square, 1 plus d plus d square, 5 times 1 plus d plus d square. Okay. In our code word, actually we only send this and either one of these. Therefore, we put a pi to denote that. We don't, if you don't put a pi, then it is a rate 1/3 code. Okay, but we are not strictly doing that. Okay, that denotes an ordering. Okay, this denotes an ordering. Okay, the coding gain of the overall concatenated code is 8. So, what is the total having the free distance for this 1/3 code? 1, 2, 3, 4, 5, 6, 7, 8. Count the number of ones. 3, 8. So, the total coding gain is 8 divided by 3. Of course, you have a code of 8, 1, 3. So, 1/3. So, that is basically 2.67. So, the coding gain is 4.26 dB. Well, not coding gain, but yeah. If you send a rate 1/3 code, that's what would be the coding gain. But the constituent code has a coding gain of, what is the defree for the constituent code, RSC? RSC coding gain is 5 by 3. That gives you about 3.97 dB. Okay, there is a difference of 0.3 dB. Difference is 0.3 dB. Okay, the defree has not changed significantly compared to even the rate 1/3 code. Right? Only 0.3 dB difference. Okay. But the major difference is the error probability is not just dictated by the defree. Remember what was the expression? WD P of D. Okay? It is these weights that matter a lot, especially in the highest analysis. Okay? So, for convolution code, it was basically FD into AD, the number of paths, path multiplicity multiplied by the number of errors that is number of ones in the, basically the number of ones in the input source sequence. Okay. Okay. The probability that defree is equal to 8 error event occurs for this turbo code is approximately 12, 2 divided by L minus 1, right, is the simultaneous probability occurrence of simultaneous error event. That's only when you make an error, right? The simultaneous error event has to happen. The simultaneous event, right? That you get d raised to m plus 1 plus the 1 plus d square type, right? On both constituent codes. And then you have this the path multiplicity factor, right? A of d into f of d. A of d is 1 in this case. There is only a single error event with defree of 8. But then f of d is, what is f of d for in this case? The input Hamming weight is 2. F of d is 2. And then q of square root of 8 times 2 by n for BPS. This is the SN. Okay? But you may say, what is about the summation over D3? Well, we are just taking the first term and approximately. Then you have to take into account the other, basically the f of d, the weight, Hamming weight of the source sequence, for higher order error rate for D3 greater than 8. Okay, so really the cool thing about TurboCodes is that in the high SNR regime, well, in any SNR regime as a matter of fact, especially if L is very large, then it goes to 0. The probability of error goes 0. But of course, unfortunately, there is what is called error flooring in TurboCodes. The probability of error decreases, and then there's some error flow occurs. Okay, but that occurs at very low error rate, so you don't have to worry about it. If you really worry about it, put an outer code of very high rate, 5/6 or something, and then bring down the probability of error to 0. But this anyway happens at very low error. Okay, so compared to convolution codes, the real nice thing, the interleaver size of the block length appears here. So you can see that D3 is just a sideshow, right? I mean, this is not going to bring it error rate to 0. And we were talking about D3 of 20, 25 in convolution codes. Okay, with very large memory, right? The shift register size was 6 or 7. But here we are talking about a 4-state code, moderately complex constituent code. 4-state code, but 2 codes operating in tandem. But decoding is not so trivial. Because we're talking about an ML decoder. So this is the magic that brings. So with this, now if you compute the performance of TurboCode, it turns out that performance comes close to capacity. Okay? So it's interleaver. It's a concatenation with interleaver. That's the trick. And decoding is just has to be done in such a way that you reach ML with reasonable performance. And luckily, such a decoder exists. So we'll show the structure of the decoder. Okay? So I will draw the structure of the decoder. The real trick is using the RSC constituent codes, because if you use the systematic feed-forward codes, that won't do the job. None of this will really happen. And a good uniform interleaver, that is also a very important aspect, and concatenation of 2 codes.
If RSC are better than feed-forward, why are they still using feed-forward?
No. RSC plays a very crucial role in TurboCodes because it's not the error event of length 1 is not the one that causes minimum distance. Error event of length 2 is the one that causes minimum distance. And because you need a polynomial 1 plus d square, and after you interleave, you want to produce something like, and this simultaneous error event probability goes something like 1 over L, whereas if you use a traditional FIR type encoder, the first error event that dictates the minimum distance event, that is d raised to m, and after interleaving you end up with some d raised to n. That's where the RSC plays a role, because it's not the single error event that causes the minimum distance. Okay. That's where it comes in. Yeah.
My question is, why people are still using systematic, non-systematic, feed-forward?
For a traditional convolutional codes, the difference, in fact, the feed-forward encoders generally do a little better at higher SNR, because as you can see, it's an error event of length 2 that gives the minimum distance. Obviously, these two factors into probability of error calculation, it increases the probability of error sometimes, in some cases.
Highest occurrence of 2 is very less.
Well, 2 is 2, I mean, and the minimum distance associated with this Well, it should be the distance spectra should be the same, right? But still, the F2 is there. See, it's not really a big deal as far as non-turbo codes are concerned. You can use a feed forward. For example, we do use feed forward memory 7 encoder, right? In traditional communication systems. For example, if you take GSM or CDMA, the constraint length is 7 and it's feed forward.
Why?
And the coding gain is very is like minimum D min is something like 20 or something per data.
We can use RSC there. RSC does better than.
See, we have already said the distance spectra of RSC and NSC are the same. So practically the error rates are in the same ballpark. All they have done is divided this by the complexity is the same, the distance spectra is the same, but it's just the weight distribution W of D that changes. So that the role of this W of D is somewhat marginal in traditional code design, right? Well, when you increase D3 very high values, like you said, it could be 2 or 1, it hardly matters. Okay, so for traditional convolutional code design, increase the number of states and find codes with good D3, job is done. Whether you do it feed forward or whether you do it in an AAR manner, it's just a choice. Okay, and some differences are there at very high rate codes as well as in the low SNR. Okay, but not really, it's not like one is achieving capacity, the other is not. But as far as turbo codes are concerned, the FIR designs are no good because we want a length greater than one error event to produce the minimum distance, and then the interleaver, when you apply it, you want a polynomial of same kind to appear, and that simultaneous error event, the simultaneous event, probably occurrence of that event, it grows like 1 over n. But if it is the first error event that causes a minimum distance of both cases, there's nothing to be done. So we have failed in the design process. That's the trick. That's the real.
Normally, when we evaluate this thing, we use AWG.
Ah.
So in AWG,
Right.
one error occurs more frequently than 2 errors.
In traditional conventional code?
No, in AWG channel.
No, we are not going to look at one BPSK symbol at a time. It's a code word, right? That we're looking. So in this case, the length 2 error event is the dominant one. That is the probability. That is the one that probability of error is dictated by length 2 error event. It's not the question of error events don't have what do you call it? We are not attaching a probability distribution to the error event. They're fixed. Length 1, 2, 3, 4, 5. They're fixed. And we are evaluating the probability of error associated with these events. Okay. So when the decoder makes an error in high SNR regime, typically 2 errors have occurred in the entire. We have a long code word. Typically 1 plus d square. That is basically 2 errors would have occurred because we are taking all 0 errors, all 0 sequence errors. That means there are 2. If you can always choose any code word as well. That we will discuss. Okay, but to make things simpler, we have chosen all 0 sequence as the reference, and then we're measuring the number of ones in the error sequence. You have to think about it a little. So really go through the derivation of probability of error of the convolutional code from the lecture as well as in TurboCodes has a good treatment of it. Go through it, try to really understand what's going on. If you don't understand that part, then you can't really appreciate this 1 over L like decay. It's very hard to really grasp this. You have to understand release first error, second error. Okay. Before we finish, we'll give you a structure for the decoder. Well, this you will be able to figure out fairly easily because you already know math BCJ. Interleaver is denoted as pi. You're going to take either one of them. So this goes through, let us say, an additive Gaussian channel with binary modulation. Just for time, it could be any modulation. Hardly matters. And it produces a sequence, right? Xk. And then you can go through decoder 1. Let's say y1k is associated with b1k. Okay? And you can run the map BCJ algorithm. Then you produce the APP estimates of dk. Okay? Then you do a de-interleaver, pi inverse. Okay? We are talking about the first code word for con. The code word associated with RSC. Then the code word associated with RSC2 is basically, well, this already gives you the APPs of dk, right? So you don't need to feed xk here. You already get the APPs, you can exploit. Okay? But you need to do some modification, which I will explain shortly. Then you can go through a decoder 2 associated with the second code, this code, and input is by 2 of k corresponding to V2 of k. Okay? And then you can get the APPs of dk again, right? And you can feed those APPs back through a feedback loop back to this is interleaver actually, because D has to be interleaved, and this is a de-interleaver, and then you feed this info back here. But if you feed the APPs of dk after the second decoding step back to this, then it is a feedback system with positive feedback. Okay? Then within the first iteration, these decisions will overwhelm this, and then the process will converge. Okay? So what you need to do is, the APPs of dk already has taken into account here xk into account, right? So, and APPs given here on dk already has taken into account xk at this input. So what you have to do is feed is what is called extrinsic information. So what you do is, L extrinsic of dk, L extrinsic of dk here, you put a hat if you want. Okay? You need to understand what this extrinsic information is. In log domain, you take the LLRs here and you subtract the extrinsic information given in the previous iteration, then you get the new extrinsic information. In log domain, you take the LLRs here, you subtract the extrinsic information given about these decays as input here. Okay? So essentially what we are saying is that this is the side information that's going to decoder 2 on the likelihoods of decay. And if you recall in map BCGR algorithm, when you calculate the transition probabilities, the probabilities, the a priori property of source bits also come into picture, right? And usually we assume them to be equally likely. But here, if you have some knowledge about the source bits from the previous iteration, you can feed it as extrinsic information. That's where it comes in. Similarly here, this decoder has improved the a priori information about decays, then you can feed it here. Okay. So the point here is that you don't want to take the LLRs here and directly feed it to this decoder, and you taking the LLRs here and directly feeding this decoder. That won't work. Okay. What you need to do is you take the LLRs here at this point, let us say, and LLRs are reflective of in this case the source bits, right? The source information about the source bit, and that is already given here in the previous iteration, and you have to take that. This decoder takes that into account, and you have to remove it from the output and feed only the incremental part to this decoder. Okay, so I'll just briefly go over this notion of extrinsic information. Then we can close this. Or do you want to read this yourself? What time is it now? Let's take map detection. We are interested in determine probability of AK equal to A given by y is some function of A which could be coded. We are not going to describe what it is. We just code it, then it's a non-trivial function. Okay. So y contains information about, and it's a sequence. Y is a sequence of observations, and we are interested in determining probability of AK taking one particular value, and A could be 0. Okay. So we're interested in determining AK hat, that is maximum argument that maximizes probability of AK equal to A given Y, and A taking values 0 and 1. That is the map detection. Okay, now we are typically interested in binary quantities. Okay, so source bits are binary. Now we define the log likelihood ratio for this binary variable A. Log LLR is defined as logarithm of probability of A equal to 0 divided by probability of A equal to 1. It's a natural logarithm basically. Okay? And the entire decoder works in log domain, and this LLRs play a very crucial role in mapping CR decoder. Okay? So now you take the sign of LLR, it tells you whether the bit equal to 0 or not. Is that right? It tells you whether P of A0 is greater than P equal to A equal to 1 and vice versa. Okay? So the detection rule is AK hat is equal to 0 if LLR of AK given by is greater than or equal to 0 and it is 1 . Okay? That is the decision. From LLR, we can get the hard decision. From LLRs, we can also get the original bit properties. This can be written as 1 minus P of A equal to 0, from which you can get the individual properties. Right? From LLR, you can get P of A equal to 0 or P of A equal to 1. Okay. So we have a sequence A1, A2 all the way to AN, the transpose. Probability of AK is equal to A given by is equal to probability of A given by for all values of the vector sequence A such that it has a kth element is equal to A. Okay, so now here this A is a vector, column vector. This A is a scalar. Okay, this is a vector. This is equal to the summation using base root probability of y. Y also is a vector, right? So we'll just put like this. Probability of y given A into probability of A divided by probability of y for all A bar such that AK equal to A. You follow this? Basically, we are talking about sequence detection. We have a sequence y, y1 to yn. It is some function of A, it's coded perhaps. And we are interested in determining the probability of AK equal to A given by just bit level probability. And that can be obtained using this general decoding. But of course, this might be probability complex. How many possibilities are there here? Right?
So this
You fix AK equal to A and then others you allow them to be 0 and 1. You have exponential complex. Of course, BCJR and BCJR tries to reduce the complexity. Okay, but this is the general. I won't illustrate the notion of okay, P of A is the a priori probability for the sequence A. Okay, in iterative decoding, this also plays a role. Traditionally, this a priori knowledge doesn't play much role in traditional decoding of convolution codes, where we assume them to be equally right? So usually the bits AK are assumed to be independent. Okay, but even in iterative decoding, the property estimates that we get, properties of AKs, we will assume it to be independent because the interleaver breaks up all the maps. So even then, this independent assumption comes in. Okay, we'll show that later. So P of A factors as the product of P of AK, K equal to 1 to some, we call it N, some N. Okay. Now the LLR associated with AK and Y that we defined, right? LLR has been defined previously. Okay? Is equal to logarithm of property of AK equal to 0 given by divided by property of AK equal to 1 given by. Property of AK equal to 0 given by is basically summation over all sequences A such that AK equal to 0, P of Y given A divided by you see all sequence A bar such that AK equal to with kth element being 1 okay. This I will write as I will exclude kth term from this. Oh, the logarithm is for the whole thing. Plus the LLR of AK. Basically, we are going to take P of AK equal to 0. Here P of AK equal to 1. We take it out. That becomes a log likelihood ratio. We get it out. Now, I'll write this above. L extrinsic AK given by plus L of this is about extrinsic information about AK in Y, and it adds to the a priori information. Okay, so after the decoder, the final LLR is this, and if you want to pass this information to the next stage in decoding, you should eliminate the a priori information that has been there. So pass only extrinsic information. Then next decoder does the same, it only passes the extrinsic information, and that extrinsic information acts as a priori information for the next stage. Okay, and usually this has the same sign as this. Usually this has same sign as this. So you should not pass the entire LLR in the iterative process. It will overwhelm the decoder and it will converge right away after the first iteration. So you won't get any control. Okay, but in the first iteration, this is 0 because the bits are assumed to be IA. So now in the turbo process, now it's fairly clear what we need to do, right? So I will redraw the structure. So this is what you need to do in implementation. And run the map BCGR algorithm in the max log mode or log map. That you can look up in one of the references. So the decoder that we propose will have the following form. Okay, this is map BCGR. It gives you LLRs on, I'll call it L of dk at the source is dk. Then I interleave it. Okay, then it goes to the next stage, decoder 2, and this becomes L bar of dk, something like that. You are interleaving. Okay, we'll call it L bar of dk. And another input is y 2k. Then you get the LLRs of dk, but then you have to subtract. This LLR will contain a priori information and the extrinsic information, and the a priori information here is L bar of I'll call it L2, and this one is L1. L2 of dk, and we will subtract with a negative sign, or we'll put a minus symbol here. Okay? And this gives us the extrinsic information. It gives us, basically this is the L2 of extrinsic information of dk, and then you go through a pi inverse, and that gives us L bar 2 extrinsic information about dk hat. We'll put hat here because there's only the estimates. Then this goes all the way back and becomes a priori information for this decoder. Okay? And this a priori information So we need something else, right? This produces L1 of dk hat, and then we'll subtract it out, then we'll get L1 of extrinsic dk hat of extrinsic L1. Okay? So in the first iteration, the side information is 0. Okay? And in subsequent iterations, whatever the LLRs you get, these are the LLRs. Okay? And you have to remove the SS information. This is in log domain. In the probabilistic domain, it's a division operation. Okay? Because in the transition branch method computation, the side information comes into picture. If you recall that, the side information is given as this extrinsic information. If you don't give the extrinsic information, if you feed the LLR directly, it will just overwhelm the decoder, and you won't get the iterative phenomenon going. And after several iterations, let us say 10 to 15 iterations, whatever the number is, you expect the entire setup to reach the maximal IQ decoder. Okay, within some gap. Okay. So from iteration to iteration, the probability of error will decrease. Okay, I want you to implement a 3GPP turbo decoder as per the standard, as specified in the standard. Okay, that is the next exercise, and your grading will depend on this as well as the map behavior on that. Okay, so I don't think there is a need for additional lecture. I'll leave you free until, let's say, the end of the month, when the grades are due at the end of the month. So I want you to implement the entire BCGR, the entire turbo decoder, encoder decoder combination using BCGR, constituent encoder, both in max log mode and full map mode, and log map mode. You can work in groups. Okay, think this. It's a fairly large piece of work. You can work in teams, but nevertheless, you should understand each and every aspect of the algorithm. The grading is based on that. Okay? And I want you to implement the algorithm with the least complexity possible and also suitable for parallelization. That is, the computation should have the least possible memory and the least possible number of add, multiply, divide, whatever it is, exponentials. You should come up with an architecture that is highly suitable for action. And these turbo codes